As a motivation for this research, consider the following problem. The 100,000 Human Genome Project is a research project that involves obtaining a complete genome of 100,000 people to study various genetic diseases. This project has recently been finished, and since a human genome consists of about 3.2 billion symbols, the size of this dataset, assuming each symbol is encoded using 2 bits, is around 75 terabytes. One of the most basic queries on such dataset asks to count or list all occurrences of a given short pattern. Due to the sheer volume of data, any solution that involves repeated scanning is too slow. Similarly, solutions based on batching the queries are not always satisfactory. To enable flexible processing of this dataset, we are interested in a solution that answers queries online. The crucial observation that allows us to efficiently handle this dataset is that genomes of two people are nearly identical. By compression, we can thus reduce the size of the data by orders of magnitude. The standard compressed representation, however, is not searchable or does not even provide efficient access to the underlying sequence. The solution to this problem is a data structure called compressed index. It allows performing queries over the original text T in space close to the compressed size of T. We can think of this as a searchable compression format. By adding the searching feature, the size of the compressed file grows slightly, but in many cases the resulting file is still orders of magnitude smaller than the original dataset. The three main lossless compression types are statistical coding. This includes, for example, Huffman and arithmetic coding. Lempel-Ziv compression. This includes the LZ77 algorithm. And Burrows-Wheeler transform, or simply BWT. As seen in the large text compression benchmark, these three methods together account for around 94% of all compressors. Large text compression benchmark is a comprehensive list and a benchmark of lossless compressors. The website was created in 2006 and is regularly updated. Currently, the benchmark includes over 200 compressors. For more details, see the provided link. For each of the listed compression type, there exists a corresponding compressed index. The index is based on the LZ77 compression, achieves space equal to the size of the output of the LZ77 compression algorithm up to logarithmic factors, and they support queries such as random access to the input text, longest common extension, and pattern search queries. The index is based on the Burrows-Wheeler transform, achieve again up to logarithmic factors space O of R, where R is the size of the output of run-length BWT compression. These indexes are more powerful than LZ indexes, since they can efficiently compute an arbitrary value from the suffix array or the LCP array. Lastly, there are indexes that achieve entropy bounds. The example space usage is the length of text times the kth order entropy of T plus a term that is sublinear in the text length. These indexes are even more powerful than the BWT-based indexes. To define the problem tackled in our paper, let us thus take a closer look at the three main compression algorithms. Statistical compression is based on encoding symbols to use varying number of bits based on the computed or predicted symbol frequencies. In the limit, these methods approach the kth order entropy of the text. Thus, they are well suited for inputs that have very skewed symbol frequencies. The drawback of these methods, however, is that the entropy is not sensitive to repetition. If we concatenate T copies of text, the output size of a statistical compressor essentially grows by a factor of T. The main idea in Lempel-Ziv compression is to explicitly locate repeating substrings in the input. Each of the repeating substrings is encoded in constant space as a pointer to the previous occurrence. LZ compression is therefore particularly suitable for inputs with many repeated substrings. These two compression methods are thus fairly well understood from the theoretical point of view, namely, it is clear what kind of redundancy they remove. BWT compression, on the other hand, is known to produce indexes that can answer powerful queries and at the same time are very small in practice. Very little, however, is understood about what is the reason these indexes are so small. In contrast to the other two methods, BWT compression is thus relatively poorly understood. We thus ask the question, what is the output size of the Burrows-Wheeler compression? The following was known about the relation of Burrows-Wheeler compression to other two compression methods until now. Recall that by Z of t we denote the output size of the LZ77 compression algorithm, by R of t the size of run-length BWT compression, and by HK the kth order entropy of text t. The first result is by Manzini, who showed that Burrows-Wheeler compression can be bounded in terms of the kth order entropy of the text. The second result is due to Geigi et al., who proved that Lempel-Ziv compression is up to log factors bounded by Burrows-Wheeler compression. In other words, we know that BWT is somewhere between LZ and entropy compression. This fact is consistent with our expectations, since earlier we have seen that if we order the indexes from slowest to fastest, or from least to most powerful, we end up with the same ordering, namely, the least powerful and slowest are the indexes based on LZ compression, and the most powerful indexes are the ones achieving the entropy bounds. Given this situation, the main question that remains is therefore, how does BWT compression compare to the other two? We are particularly interested to know whether BWT compression is provably close to LZ compression, since this is the effect that was observed in practice. The commonly conjectured answer to this question was no. The argument against such connection is that BWT-based indexes can support suffix array queries, and Lempel-Ziv compression is not related to the structure of the suffix array. We are now ready to state our results. Our first main result is that Burrows-Wheeler compression can be bounded up to log factors in terms of Lempel-Ziv compression. This answers the previous question in a much more surprising way than anticipated and immediately implies a number of other results. For example, it proves that we can support powerful suffix array and suffix tree queries in space close to O of z. It also implies optimal time algorithms for many problems on strings, assuming only that the input text is weakly compressible by LZ77. Our second main result is the algorithm to convert the LZ77 compressed file into run-length BWT compressed file running in time that is roughly proportional to the size of the compressed file. Compared to the previous algorithms, ours achieves an exponential speedup. To achieve this result, we introduce a number of new techniques of independent interest. In this talk, we will focus on the first main result. We will see a complete proof of this upper bound. Let us formally define LZ77 compression. The key concept in LZ77 is the longest previous factor, or LPF. The LPF of I is the longest substring starting at position I that has another occurrence starting at some position j smaller than I. Note that LPF can be encoded in constant space as a pair containing its length and the position of the previous occurrence. In the example, the LPF at position I has length 4. The LZ77 compression is defined as follows. Given a string t of length n, we greedily, that is left to right, partition it into LPFs or single symbols if the LPF has length 0, and then output the encoding of each LPF or a single symbol as a pair. By z of t, we denote the number of pairs in the output. In the example, suppose we have already partitioned this string up to position 11. At this point, we take the LPF at position I, which in this case is a substring of length 3 starting at position I, with an earlier occurrence at position 7, and encode it in the output as a pair of integers containing length and the position of the earlier occurrence. Next, we look at position 15. In this case, the LPF has length 5, and an example occurrence starts at position 5. We thus append the pair 5, 5 to the output. This concludes the compression algorithm. the value of z of t for this string is 7, as the output consists of 7 pairs. Let us now define the BWT compression. Let t be a string of length n. We assume that the last symbol of t is a special sentinel symbol denoted with a $, that is strictly smaller than all other symbols in the text. The Burrows-Wheeler compression is defined as follows. We start by lexicographically sorting all suffixes of the text. We denote the starting position of the ith lexicographically smallest suffix as SA of I. The name SA stands for suffix array. For example, since the lexicographically smallest suffix is the one starting at the last position of the text, we always have value n as the first element of the suffix array. For this text, the lexicographically second smallest suffix of text is the one starting at position 19. Therefore, the second value in the suffix array is the value 19. We can now formally define the Burrows-Wheeler transform. For any I between 1 and n, we define the BWT of I as the symbol immediately preceding the lexicographically ith suffix of text t. Formally, if SA of I is greater than 1, then the BWT of I is the symbol at position t of SA of I minus 1. In the special case of suffix array having value 1, we define the BWT at position I to be the $ symbol. The BWT of the example string looks as follows. It is easy to see that BWT is a permutation of the input string. The important property of BWT is that it is an invertible transform, that is, given the BWT, we can restore the original string. The last step of BWT compression is to apply run length encoding on the BWT, that is, we represent every block of equal symbols using a pair of integers denoting the symbol and the length of the block. By r of t, we denote the number of runs in the resulting encoding. The resulting runs for the BWT of the example string look as follows. Thus, if we represent each one as a pair containing its length and the symbol in the run, we obtain the following encoding of the BWT. Since there is 8 runs in the encoding, the value of r of t is 8. We are now ready to present the proof of the main result of our paper, namely that r is at most O of z times log squared of n. For any index I between 2 and n, we define the LCP of I to be the length of the longest common prefix between suffixes starting at position SA of I and SA of I minus 1. For completeness, we define LCP of 1 to be 0. In the example, the LCP of 8 is equal to 3, since the corresponding two adjacent suffixes in the suffix array share a common prefix of length 3. We call LCP of I irreducible if either I is equal to 1 or BWT of I is different from BWT I minus 1. In other words, irreducible LCPs are the LCPs between suffixes which are on the boundary of runs in the BWT. The following lemma holds. The sum of all irreducible LCPs having values in the interval from L to 2L is bounded by O of z times L times log n. We will prove this lemma on the following 2 slides. Observe that the above lemma is all we need to prove our main result. First, recall that the number r of runs in the BWT is equal to the number of irreducible LCP values. We classify all BWT runs into log n buckets based on the value of their corresponding irreducible LCP value. More precisely, we consider intervals of the form from Li to 2 times Li, where Li is equal to 2 to the I for all I between 0 and log n. This way, every irreducible LCP is accounted. The number of elements in a bucket is maximized when all values are as small as possible. Even when they are as small as possible, there can only be z log n of them in a single bucket. To account for LCP values equal to 0, we observe that their number is bounded by the alphabet size. The latter is no more than z, since there is at least one phrase for each different symbol in the text. What now remains is to prove the above lemma. The proof of the main lemma is achieved in two steps. First, we need to establish the following very simple observation about LC77 parsing. We claim that for any L bigger or equal than 1, the number of distinct substrings of length L is at most Z times L. To prove this, consider any substring S of length L. Then, as long as S is inside some LC77 phrase, map it to an earlier occurrence. Assuming this is the LC77 parsing of the input, in this case the substring S is inside of the phrase of LC77. By definition of the parsing, this phrase has an earlier occurrence in the text. This implies an earlier occurrence of the substring S. We then repeat the process. In this case, we again landed inside the LC77 phrase. Repeating this step, we will eventually find an occurrence of S that overlaps two LC77 phrases. It remains to observe that since there is at most L ways to position a string of length L so that it overlaps two phrases, we obtain that there can only be at most Z times L different substrings of length L. We now move to the proof of the main lemma. Let us take some LCP of I with a value inside the interval L to 2L and assume that this LCP is irreducible. Denote the set of all substrings of text of length M as Sm. In the definition we use T infinity, which is defined as the string consisting of infinite number of copies of T. For every such LCP, we assign a cost L and distribute it among symbols of strings in the set S3L. In other words, with each such LCP, we will repeat L times the process of choosing some substring of T of length 3L and choosing some position of that substring. The assignment is done as follows. The value LCP in this figure are marked in green. The BWT symbols are colored blue and red. Since LCP of I is irreducible, there is a run boundary at position I. Consider some split point among the first L positions. Then, in rows I-1 and I, look L positions to the left and 2L positions to the right. We will select one of those substrings. Let us call them X and X prime. We assume that the missing symbols of the substrings are given by extending all suffixes both ways, as in the string T infinity. Once we select one of those strings, we have to select its position. We will always select the position that intersects the BWT column. To make the decision about which of these two strings to choose, consider a trie T containing all reversed substrings of length L of text. In this tree, we define any edge connecting a vertex V to its parent P of V as light if V has a sibling such that the size of this sibling, defined as the number of leaves in the subtree, is greater or equal than the size of V. To choose one of the strings among X and X prime, let K be a position such that X of K is the character intersecting the BWT column. In this example, the value of K is 2. Let us now look at the nodes in the trie T that spell the substrings starting in X and X prime at position L and going backwards to position K. In this example, we would look at the string with symbols BAB and BAA. These two strings are marked in the tree. Of these two strings, we choose the one that traverses the light edge at the point where the two paths split. In this case, the red edge is light, and hence we choose the substring spelling the path from the root BAA. This concludes the description of the way we select one of these two strings. Recall that since for each LCP we need to assign a cost L, we repeat this step for all possible split points of the first L symbols. For example, when placing the split after the third character and extending L symbols to the left and 2L symbols to the right, we find that both paths end with a light edge. In this case, we can choose any of them. When placing the split after the first character, we find that the light edge is the one corresponding to symbol A. We claim that each string in the set S3L is charged at most 2 log n times. Consider some string y from the set S3L. Since we always charged the position intersecting the BWT column, only symbols of y at positions from 1 to L can be charged. Observe that whenever y of k is charged, the last edge on the string spelled by going backwards from position L to position k is light. In this case, if A was charged, that meant that the red edge was light. Similarly, B can only be charged if the blue edge is light. The same holds for every character from position L to 1. Observe that all these light edges need to lie on a single path in the trie. In this case, we have 2 light edges, and hence 2 symbols would be charged. Therefore, since the number of charged positions in Y is less or equal than the number of light edges on a single path in T, this number is bounded by log n, since whenever we traverse a light edge, the size of the current subtree is divided by 2. We have thus shown that the number of positions that can be charged in a single string is at most log n. We will now show that each individual position can moreover be charged at most twice. Let y as before be a string in the set S3L. Consider some position k between 1 and L, and let y prime be the string extending from position k plus 1 until the end of the string. We aim to show that y of k can be charged at most twice. For this, observe that whenever y of k is charged, 2 things are always true. First, the string y is a prefix of either the suffix starting at position sa of I-1 or suffix starting at position sa of I. In the example, we see a situation where y prime is a prefix of the suffix starting at position sa of I-1. The other figure shows the other case. In both cases, we also have that LCP of I is less than 2L. Consider all suffixes of the text that are prefixed with the string y prime. By the argument seen on the left side, the indexes I for which the symbol yk can be charged have to be very close to this range of suffixes. Namely, they either have to be inside or one position after. Observe, however, that the length of y prime is at least 2L. Thus, out of all these candidates, there are only 2 positions for which the LCP value can be less than 2L. We have therefore proved that each of the strings in S3L can be charged at most 2 log n times. It remains to observe that since all LCP values we consider are between L and 2L, and for each we charge a cost of L, the total sum of all considered LCPs is no more than twice the charged cost. The latter quantity is bounded by the size of the set S3L times 2 log n. It remains to recall the observation about LZ77 that the number of distinct substrings of length m is at most m times z. Applying this to the set S3L, we obtain the final upper bound. This concludes the talk. We have presented a proof that the value of r is up to log factors bounded by the value of z. In the paper, we also describe the first algorithm able to convert between LZ77 compressed text and BWT compressed text in time that is essentially proportional to the size of compressed data. In addition to these main results, we obtain a number of auxiliary results. This includes other bounds, such as the first bound relating the value of r for the text and its reverse, and a set of new data structures and indexes that are of independent interest. Future work includes proving the tightness of our bounds, reducing the log factor in the runtime of our algorithm, and designing practical algorithms for converting between compressed representations. Thank you for listening to this talk. The full paper can be found at the following address.